Right, so differentiating implicit functions is one of the more awkward topics in advanced higher maths. Okay, so implicit functions you've not really dealt with at all yet, so we're just going straight into actually differentiating them. You will have kind of noticed, you will have had implicit functions, but you won't necessarily realize that they're implicit. The kind of clue comes from the name. So generally we deal with a function like this, in which case it's explicit. Okay, it's explicitly telling us that y is minus 3/4 of our x plus 6. If we had something like this where 3x plus 4y equals 24, that's implicit. Okay, so they're both exactly the same equation, but obviously one's explicit and one's implicit. Okay, the point being that when we want to differentiate it, okay, generally when we're differentiating, pretty much every time that we've differentiated up until this point, we've had a function y equals something. That doesn't mean that obviously functions don't exist that aren't just y equals. Okay, and they're going to, basically we're going to actually differentiate some that are a lot more difficult than this. The thing with this one is that we can actually rearrange it so that it is y equals. Okay, but the ones that we're going to be dealing with, we can't rearrange. We have to deal with them as they are. We still want a derivative for that function for one reason or another. Okay, so it generally revolve around a circle. So implicit functions, when we've got things involving x's and y's that can't necessarily be explicitly stated. Okay, this one kind of can in a way, but the ones that we're going to be looking at in the next couple of examples can't. So it's generally dealing with circles. So it's going to come into play later on in terms of when we're dealing with stationary points and things. Okay, so if you remember, I did discuss this in class. But if you're still stuck on the idea, then just come and see me. It's not necessarily going to come up that often, so I don't need to explain it on this. But we're getting away from kind of lines in terms of a continuous left to right function. And what might happen now is we're dealing with circles and, as I said in class, ellipses. So basically what we're doing here is going to find a gradient of the tangent at a certain point to the circle with equation x squared plus y squared equals 25. Okay, so again, nothing about differentiation, but we know if we're dealing with gradients of tangents, then that's what we need to do. Okay. So what have we got here? As we are simply adding together two terms, we don't need to worry about chain product quotient rules. So none of that actually comes into play here, but we do need to differentiate y squared, which you haven't necessarily done yet. Okay, this is just to get us used to the idea of differentiating like y squared. Right, don't think of y in terms of a constant. So perhaps in the past when you've differentiated something like x squared plus a, you've just neglected the a, just knowing that it was a constant. Y squared here is not a constant. Okay, y is not a constant, y squared is therefore not a constant. Okay. So we have to think a little bit more carefully. So the way I'm going to do this at the start, I'm going to show you this in a little box to one side. Right? Once you get used to this, you don't have to do it like this, and you're going to see some kind of patterns emerging, some kind of shortcuts almost to be able to do stuff like this. But this is just explaining where it all comes from, obviously, so we can kind of utilize it in a further sense later on. Okay. So the best way to think of it is think of y squared as a whole separate function. And then what we're going to basically do is we're going to apply something along the lines of the chain rule to it. Okay. So I'm going to let z equals y squared here. Okay. Knowing full well that with the chain rule, if I had something like z, in which case I wanted to find dz by dx, because that's what I'm doing here. I'm still going to differentiate this with respect to x. I'm not differentiating it exactly in terms of y. I still want to differentiate the function z equals y squared in terms of x. So from this function, I want to find dz by dx. If you remember how we write the chain rule, we can say that dz by dx is the same as dz by dy times by dy by dx. In other words, the dy's cancel out. Okay, so I'm going to use that knowledge. I'm going to use that to help me find dz by dx here. Okay, so all I need is to find dz by dy. Okay, so I am actually going to differentiate this with respect to y. Okay, so just in the same way, imagine it was x squared and I was differentiating it in terms of x. It would be 2x. If it's y squared and I'm differentiating in terms of y, it would just be 2y. But the point is, from this, I need to actually then multiply it by dy by dx. Okay, and I literally just do that. I just actually write it dy by dx. At the end of the day, what I want in my answer is I want a dy by dx. Okay. You've basically got accustomed to taking a function and changing the y and just writing dy by dx underneath for the derivative. Okay, it's the same kind of idea here. Okay, but what we're actually doing, what we've always done is we've found the derivative of y. The derivative of y is dy by dx, or at least it's the representation of it. Okay, it's the notation of it. Okay, so we're taking our x squared plus y squared equals 25, and then we're differentiating each part. Okay, so x squared, remember we're differentiating with respect to x. X squared just becomes 2x, just normal. And what I've done over here is I found the derivative of y squared. Okay, derivative of y squared is 2y times by dy by dx, and that equals, and I have to make sure I do deal with the right hand side. A lot of people neglect this. More often than not, it will be a number, in which case it will just disappear like this one, but you still have to write something in. That equals 0, okay? And what we basically want to do is we want to rearrange this to give a function in terms of dy by dx. Okay? Because I'm actually going to find the gradient in a second, I still need to know what dy by dx is in a function in itself. So what I'm going to do is rearrange this. Okay, move the 2x over, in which case it becomes 2y times by dy by dx equal to minus 2x, and then I'm going to divide by 2y. Simplify if I can. In this case I can. It just becomes minus x over y. Okay, so that is my derivative. Okay, I've just got to apply it to the question. So I'm finding the gradient of the tangent at a, which is 3 minus 4. So I just shove those values in, and I get minus 3 over minus 4, which obviously simplifies to 3 over 4. Okay. But that's a more straightforward example of implicit differentiation. So let's try a more difficult one. Okay, so for the curve with equation x cubed minus xy plus y squared equals 1, we're going to express dy by dx in terms of x and y. Okay, so we're just going to find the derivative of this function, which can't be explicitly stated. Okay, so I couldn't rearrange this in any way to just give me y. So I have to deal with the fact that I've got y's all over the place here. Okay, and there's a couple of things to consider here. Namely the fact that I've got x times by y here. Okay, it may look straightforward, but it's a more complicated one to consider, because what it actually is it's two different functions in terms of x multiplied together. Okay, so in which case I'd have to use the product rule. Sorry. So again, I'm going to use a little box at the side. I'm going to focus on differentiating xy with respect to x. Okay. So because, as I say, it's a chain rule, I need to split into the two functions, f of x equals x, g of x equals y, and I'm going to differentiate each one individually. So f dash x is obviously just going to equal 1, and g dash x, okay, the derivative of y is just dy by dx. Okay, now I need to apply the product rule. So f dash g plus g dash f, which is 1 times y bar, 1 times by y plus dy by dx times by x, which simplifies to just y plus dy by dx x, or x dy by dx. Okay. The y squared, okay, we did in the previous one. It's just 2y. Okay, so it's the function differentiated with respect to y, which is 2y times by dy by dx. X cubed is easy. It's just old school differentiation, in which case it's 3x squared, and just remember the 1 also differentiated. So 3x squared, first bit differentiated, minus, that's what we got for the derivative of xy, plus the derivative of y squared was 2y dy by dx. It was explained in the previous slide, and the derivative of y is just 0. Okay. Right, so again, same as before, we want to get a function that's explicitly, this time in terms of dy by dx. Okay, but because I've got two of them, I'm going to need to gather them together and factorize a little bit. Okay, so just simplify the brackets out first until you get something like this. Move everything that's not dy by dx over to the right-hand side. So I'm taking away 3x squared, and I'm adding on y, in which case it's y minus 3x squared. And I'm trying to get the dy by dx by itself, so I'm taking it out as a common factor, in which case I'm left with 2y minus x in the brackets, and I'm going to divide both sides by that. Okay, doesn't look great, but if you were given a point like we were in the last one, it's just a case of putting some numbers in. Okay, but generally you'll find that these functions end up, in terms of the derivative at least, as a function in terms of x and y. Okay, right. Next example, okay, so obviously we can do this in terms of trigonometry and logs and exponentials, so we need to be able to take care of that. So just bringing everything together here, but just be careful. We've got y sine x here, so it's a product rule. EY, just be careful of your different rules for differentiating exponentials. Okay, still go through it as normal. Okay, so I'm going to do a little box to the side so I can take care of the y sine x. F of x equals y, g of x equals sine x. Okay, so then the derivative of y is dy by dx, the derivative of sine x is cos x. Applying the product rule, I get dy by dx times by sine x plus cos x times by y. Be careful how you write this. Don't write this as cos xy. There's some of you doing that before. If it's cos xy, that implies it's the cos of x and y, or the cos of x times by y. This very specifically has to be written like this. Okay, don't confuse yourself, or don't confuse the person who's marking it. Y cos x plus sine x dy by dx. Okay, to be honest, that probably should be at the front as well. Hey ho, right. The EY, okay, so we're differentiating. Remember the first one I showed you, it's in terms of the chain rule. So you differentiate it with respect to y, which is just e to the y, and then you times it by dy by dx, okay? The derivative of 22 is just 0. So again, we're going to have to move everything that's not dy by dx to the right-hand side, so that we can take dy by dx out as a common factor, and then just divide by what's left. Okay. Right, next up, second derivatives of implicit functions, which I'll do in a separate PowerPoint. Okay.